The energy in a wave, amplitude. Amplitude is the height or strength of a wave, indicating the amount of energy it carries.
Imagine trying to communicate with someone across a crowded room at a party. The louder you speak, the more intense your voice becomes, allowing it to travel further and be heard over the ambient noise. Similarly, in a wave, the amplitude represents the energy it carries, determining how far and effectively that energy can travel. Just as speaking louder helps your voice reach the listener, a wave with a higher amplitude has more energy, enabling it to transmit its effects over greater distances.
The highest point of a transverse wave crest. The wave crest is the peak or topmost part of a wave.
Imagine trying to balance a spoonful of soup while walking across a crowded room without spilling it. Just as the soup in the spoon reaches its highest point, when you carefully lift it up to avoid obstacles, a wave crest represents the peak or highest point of a transverse wave. The soup balancing at its peak is like the wave crest, both representing the maximum point before gravity, or, in the case of a wave, energy pulls it down again.
The bending of waves when they pass around a barrier or through an opening. Diffraction. It's when waves change direction and spread out as they go around obstacles or through small gaps.
Imagine you're walking down a street and smell the delicious scent of freshly baked bread coming from a bakery around the corner. Just like how the aroma manages to reach you, even though the bakery is not directly in your line of sight, waves can bend around barriers or pass through openings, spreading out in new directions. This is similar to diffraction, where waves, like light or sound, bend around obstacles or spread out after passing through an opening. Just as the scent of bread diffuses into the air and reaches you despite the barriers.
The number of cycles or vibrations per second, measured in hertz. Frequency. It is how often something happens in a specific period of time, like how many waves pass a point in 1 second.
Imagine you're sitting in a busy coffee shop, trying to hold a conversation with a friend, but the constant chatter around you makes it difficult to focus. This situation is similar to the concept of frequency, because just like the number of conversations happening at once, frequency measures how many cycles or vibrations occur in a second. In this analogy, each voice in the coffee shop represents an individual cycle or vibration, and the more voices there are, the higher the frequency of sound you perceive, just as a higher frequency in hertz means more cycles or vibrations per second.
Occurs when two waves meet and combine to form a new wave. Interference. In simple terms, interference happens when waves overlap, creating a new wave pattern.
Imagine you're at a party where two different conversations are happening at the same time, and you're trying to listen to both. This situation is similar to wave interference, where two waves meet and combine to form a new wave, either amplifying or canceling each other out. Just like how your brain might mix the voices into a confusing blend or pick up louder snippets from one conversation, interference occurs as the waves overlap and either enhance or diminish each other, creating a new wave pattern.
The substance through which a wave can travel, like air, which carries sound waves, is called a medium. In science, a medium is the material that carries waves, such as air, water, or solids.
Imagine trying to pass a message across a crowded room at a party without shouting. Just as you rely on people who act as intermediaries to relay your message, a medium like air carries sound waves from one point to another. In this analogy, the people in the room are akin to the air molecules that facilitate the movement of sound, ensuring your words reach their destination despite the noise.
The least dense region of a longitudinal wave rarefaction. Rarefaction is where particles are spread apart in a wave, creating a low pressure area.
Imagine you're in a crowded elevator, and as it stops at a floor, a few people step out, giving everyone a bit more breathing room. This moment of relief, where there's suddenly more space and less pressure, is similar to the concept of rarefaction in a longitudinal wave. Just as the elevator becomes less crowded when people leave, creating a region of lower density and pressure, rarefaction occurs in a wave when particles are spread apart, creating the least dense part of the wave.
The bending of light when it passes from one substance into another. Refraction. Refraction is the change in direction of light as it moves between different materials like air and water.
Imagine you're walking through a park and suddenly encounter a muddy path that slows you down and changes the direction you're heading. This situation is similar to how light behaves when it moves from air into water, bending and altering its path due to the change in medium. Just like your feet slow down and change direction when they hit the mud because it's harder to walk through than grass. Light slows down and bends when it moves from air, an easier medium, to water, a denser medium, illustrating the concept of refraction.
An increase in the vibration amplitude of an object caused by another object vibrating at the same frequency. Resonance occurs when an object vibrates at the same natural frequency as another, causing it to vibrate more strongly.
Imagine trying to push someone on a swing. If you push at the right moment, they'll go higher and higher. This is similar to resonance, where an object increases its vibration amplitude when another object vibrates at the same frequency. Just as timing your pushes with the swing's natural rhythm makes it soar higher, when two objects share the same vibration frequency, one can amplify the other's motion, leading to increased energy and movement.
A wave that seems stationary, it forms when two waves of equal wavelength and amplitude cancel each other out. Standing wave. In simple terms, a standing wave is a pattern created when two identical waves pass through each other, appearing to stand still.
Imagine you're trying to balance a seesaw with two people of equal weight sitting at opposite ends. This situation is similar to a standing wave because just as the seesaw remains level and stationary when both people balance each other out, a standing wave appears stationary when two waves of equal wavelength and amplitude travel in opposite directions and cancel each other out. The seesaw represents the medium, like a string or air column. The people are analogous to the waves, and their balanced state mirrors the stable, stationary pattern of a standing wave.
A wave that moves particles of matter at right angles to its direction of travel. Transverse wave. A transverse wave is like a sideways ripple, where energy moves forward while particles vibrate up and down.
Imagine you're at a crowded concert trying to push your way through the throng of people to get closer to the stage. Much like your struggle to move forward while people are jostling side to side, a transverse wave moves particles of matter at right angles to the wave's direction of travel. Just as your forward movement is affected by the lateral movements of the crowd, in a transverse wave, the particles move up and down or side to side, perpendicular to the wave's forward motion, much like the crowd's sideways shifts as you try to advance.
The lowest part on a transverse wave is called the trough. A trough is the point where the wave is at its minimum displacement from the rest position.
Imagine you're trying to find the best time to shop in a busy supermarket to avoid the crowds. This scenario is similar to identifying the trough in a transverse wave, which is the lowest point, just like finding the least busy shopping time. Just as you look for the lull in shopper activity to enjoy a quieter experience, the trough represents the point in the wave where the energy is at its lowest, akin to the supermarket being at its emptiest.
a repeating disturbance that transfers energy through matter or space. Wave. In simple terms, a wave is a way energy moves from one place to another, like how ocean waves travel across the sea.
Imagine trying to pass a message across a crowded room without moving from your spot. Just as you would need to rely on a series of people repeating your message until it reaches the intended recipient, a wave transfers energy through a medium by passing it along from one particle to the next. In this analogy, each person represents a particle in the medium. The message is the energy. And the act of passing the message along is akin to the disturbance that travels through the medium, illustrating how waves transfer energy across distances.
The distance between the crests of two adjacent waves. Wavelength. Wavelength is the measurement of the length from one peak of a wave to the next peak.
Imagine trying to find the rhythm of footsteps on a crowded sidewalk, where you're trying to match your pace with others to avoid collisions. Much like gauging the distance between each step to maintain a smooth walk, wavelength is about measuring the distance between the peaks of each wave. Just as consistent spacing between your steps helps you move fluidly, the consistent distance between wave crests determines the wave's frequency and energy, ensuring it travels smoothly through its medium.
A wave that needs matter to travel, like sound waves and ocean waves. Mechanical wave. A mechanical wave is a type of wave that requires a medium to propagate, like air, water, or solid material.
Imagine trying to send a handwritten letter to a friend, but you don't have a postal service to deliver it. Just like the letter needs a mail carrier to reach its destination, a mechanical wave requires a medium, such as air, water, or solid matter, to travel through. In this analogy, the postal service represents the medium, the letter is the wave, and the delivery process is how mechanical waves, like sound and ocean waves, propagate by moving through matter.
A wave whose particles vibrate parallel to the direction in which the wave travels. Longitudinal wave. In a longitudinal wave, particles move back and forth in the same direction as the wave travels, like sound waves in the air.
Imagine trying to squeeze through a crowded hallway where everyone is walking in the same direction as you are moving. This scenario is similar to a longitudinal wave, where particles in the medium move parallel to the direction the wave travels. Just like how people in the hallway move forward by jostling each other forward, particles in a longitudinal wave, such as sound waves, push and pull on each other in the same direction as the wave's movement, creating areas of compression and rarefaction as the wave propagates.
Part of a wave where particles are pushed together. Compression. Compression is when particles in a medium are squeezed tightly together, creating a region of higher pressure in a wave.
Imagine being in a crowded elevator where everyone is pressed closely together. This situation is similar to the compression part of a wave, where particles are pushed together tightly. Just like how people in the elevator have less space to move and are packed in a confined area, compression in a wave involves particles being squeezed closely together, reducing the available space between them.
The bouncing of light, sound, or heat waves off a surface. Reflection is when waves, like light or sound, hit a surface and bounce back.
Imagine you're trying to have a conversation in a crowded, echoey restaurant. Just like how your voice bounces off the walls and returns to you, creating an echo, light, sound, or heat waves also bounce back when they hit a surface. In this way, just as your voice reflects off the walls and returns to your ears, light reflects off a mirror and returns to your eyes, or sound waves bounce off a surface and return, creating an echo.
states that the angle of incidence is equal to the angle of reflection. Law of reflection. In simple terms, the law of reflection explains how light bounces off surfaces in a predictable way.
Imagine you're playing a game of pool, trying to sink a ball into a pocket by bouncing it off the table side. Just like when you aim the ball at the cushion and it bounces off at the same angle, light behaves the same way when it hits a mirror. In this analogy, the pool ball is like a beam of light. The cushion represents the mirror, and the way the ball bounces off at an angle equal to how it hit is just like how light reflects off a surface, illustrating the law of reflection where the angle of incidence equals the angle of reflection.